Welcome back to the Deep Dive, the show where we take stacks of fascinating information and really try to distill them into clear, engaging insights.
And today, we're diving into something pretty fundamental, aren't we?
We really are. We're tackling one of the most pressing global challenges.
Mhm.
How do we ensure a reliable, clean energy supply, especially, when those intermittent sources like solar panels and wind turbines aren't always generating power?
It's truly the Gordian knot of our energy transition.
Mm.
The world is racing towards net zero emissions.
Mm.
Renewables are booming, getting incredibly cost-effective.
Which is great news.
Absolutely.
Right.
But their inherent variability, sunshine fades, wind dies down, it creates this fundamental imbalance. We simply can't rely on them 24/7 without a robust way to store that energy.
Precisely. And that's our mission today. To cut through the noise, illuminate a fascinating, maybe often overlooked solution to this energy dilemma. And we're drawing from a groundbreaking piece of research.
Yeah.
We are taking a deep dive into an assessment titled Assessment of Geological Resource Potential for Compressed Air Energy Storage in Global Electricity Supply. It's quite a title, but it's a study that truly unpacks this massive potential right beneath our feet.
Hidden potential, really.
So let's unpack this urgent need for energy storage a bit more. Renewables, as you said, getting cheaper, fantastic for meeting those net zero targets, the ones largely set back at COP21, the Paris Agreement.
Mhm.
But their output is so variable. I mean, wind farms, what do they operate at? Like 20–45% capacity typically?
Yeah, somewhere in that range. And solar's even lower, maybe 10–23%.
Right. So that creates this huge gap between when energy is produced and when we actually need it most.
That gap is critical, and it's exactly where compressed air energy storage, or CEES, steps in as a potentially powerful utility-scale solution.
Okay, CEES.
Its core function is elegantly simple, actually. It stores excess, low-value power generated during off-peak hours.
Electricity that might otherwise just go to waste.
Precisely. And then it releases that stored energy during peak demand periods, when the grid really needs it. Think of it like a giant geological battery.
A giant underground battery. And this isn't just theory, right? This is actually happening.
Oh, absolutely. We have real-world examples already in operation, humming along quietly for decades.
Like what?
Well, the first commercial CES plant, Huntorf, in Germany.
Yeah.
It's been running since 1978.
Wow, since 78.
Yeah, it's a significant plant too, 290 megawatts. Operates at about 42% efficiency. Then in 1991, the McIntosh plant in Alabama, USA came online.
Okay.
That one's 110 megawatts, but they made a key improvement there. They included a heat recuperator.
What does that do?
It boosted its efficiency up to 54% by basically reducing the fuel consumption by about 22–25%.
Ah, so better efficiency.
Exactly. And what's really striking, and a key point this study emphasizes, is that apart from pumped hydro energy storage, PHESCS, is currently the least cost utility-scale bulk storage system available.
Loose cost after pumped hydro. It's a pretty big deal economically.
It's a huge advantage.
Now, this study, it really digs into two types of CS, doesn't it? There's diabatic, DCAS, and adiabatic, KCS. Can you walk us through that difference, especially why ACS seems so interesting?
Certainly. So DCA is the diabatic kind. That's what those existing plants at Huntorf and McIntosh are. It works by compressing air into underground caverns using electricity. Pretty straightforward.
Okay.
But then to generate power, it has to heat that compressed air using natural gas combustion before it expands through the turbine.
Ah, so it still uses fossil fuels in that step.
Exactly. But ACS, the adiabatic type, this is where it gets really interesting and quite innovative. Instead of just wasting the heat that's naturally generated during the compression process.
Right, compression makes things hot.
Precisely. ACS captures that heat, stores it, and then re-injects it during the discharge phase when the air is expanding.
So you get the heat back into the system?
You get it back.
Okay.
And this completely eliminates the need for burning fossil fuels like natural gas in the generation step.
Which makes
A truly CO2-neutral peak load solution. And you can reach really impressive efficiencies, potentially up to 70%.
70%. Wow. Compared to the 40s and 50s for the older plants.
It's a significant leap. And there are projects testing this, like the Adele project in Germany, a pioneering ACES demonstration plant.
So just to recap, the older plants needed natural gas to reheat the air, but this newer ACAs captures its own heat from compression and reuses it. No fossil fuels needed for generation. That's a massive step forward, isn't it?
It really is.
So what does this all mean for you, our listener, when we talk about shifting to more reliable, cleaner energy?
Well, it means we're moving towards a future where The stop-start nature of renewables doesn't have to be such a roadblock. ACES especially offers a way to smooth out those peaks and valleys in wind and solar generation.
Making the grid more stable.
Exactly. Ensuring a stable, cleaner energy flow to your homes, to businesses. It's about making a fully renewable grid not just a possibility, but actually dependable day to day.
Okay, so we've got the why CES is important. Now let's shift gears to the how. Specifically, how this particular study, the Assessment of Geological Resource Potential. How did they manage to map out the Earth's hidden storage potential? It sounds like a massive geological treasure hunt.
It really was a monumental task. This study performed a comprehensive global estimation. I mean, think about the scale.
Yeah, the whole planet.
The whole planet. So, to manage that scope, the researchers meticulously divided the world into 9 major regions. And then they went even further, subdividing those into 145 subregions for incredibly detailed analysis.
Wow, 145 subregions. That's granular. How did they actually pinpoint the right geological spots? Were they looking for specific rock types?
Yes, they employed a pretty sophisticated methodology, identifying suitable geological formations by, and I'm quoting here, overlaying suitable geological formations, salt deposits, and aquifers.
So layering different maps together.
Kind of like digital layers, yeah. Using a combination of global and country-specific geological maps to pinpoint these likely locations. Then, to actually quantify the potential storage volume.
Right, how much space is down there?
They made some key assumptions about the cavern design. They modeled cylindrical caverns, think giant underground tanks, with a surface area of 25,000 square meters and a volume of 270,000 cubic meters.
Yeah, where did those numbers come from?
They were based directly on the real-world specifications of the Huntorf plant in Germany, so grounded in reality.
Okay, makes sense. And then there's this thing they call the 1% rule in this study. That sounds maybe a bit arbitrary. What's that about?
It might sound like it, but it's actually crucial for realism. The assessment implemented 3 constraints, allowing for 1%, 5%, and 10% of the selected area to be considered for AIEs.
Okay.
But they often highlight the 1% results. And this is really important. It accounts for real-world construction constraints. You can't just dig a massive cavern anywhere you find suitable geology, right?
No, I guess not. There could be towns, infrastructure, parks.
Exactly. Or maybe just practical difficulties. So that 1% rule ensures the estimations are conservative, achievable, not just theoretical maximums.
Got it. So it's a reality check built into the numbers. Once they had this potential volume mapped out using the 1% rule, how did they translate cubic meters of space into actual energy storage, like megawatt hours?
Right, the useful metric. They translated the estimated cavern volume into energy capacity by multiplying it by a specific factor, a weighted average of 0.00028 megawatt hours per cubic meter.
Okay, another specific number. Where did that come from?
Again, derived directly from the real-world energy capacities and volumes of the 2 operational plants, Huntorf and McIntosh.
So they're consistently basing their calculations on what's already proven to work.
Precisely. It grounds the entire global projection in actual demonstrated performance.
That's clever. Okay, so now we understand the how of the mapping. Let's decode the ideal geologies. This study highlights 3 main types of underground formations that work well for seas.
Yes, the big 3 are salt formations, hard rock, and porous rock. And it's worth noting, just for context, this study found that roughly 75% of the United States, for example, has geology suitable for some kind of CHEs.
75% of the U.S., that's
Yeah.
a lot of potential area.
It really is. It gives you an idea of how widespread the possibilities might be.
Okay, let's start with what this study called the gold standard, salt formations. Why are they considered the best?
Well, salt deposits, especially those big underground mounds called domal salt formations, are considered the best option and low risk. And it's no coincidence. This is exactly where Huntorf and McIntosh are located.
Ah, the existing plants chose salt.
They did. And creating the caverns is pretty cost-effective. You use a process called solution mining, basically pumping water down to dissolve the salt and pumping the brine out, leaving a cavity. The study estimates the capital cost around $2,000 USD per megawatt hour.
Relatively cheap for large-scale infrastructure.
Comparatively, yes. And what's really fascinating, something this study points out, is this natural synergy in some places. Yeah, there's a significant coincidence, a geographical overlap, between areas with high wind potential and these ideal salt domes, particularly in parts of Europe and North America.
Wow, so the wind power source is right near the perfect storage spot.
Sometimes, yes, that's like nature set it up perfectly in some locations.
That's incredible. Okay, what about the next one? Porous rock, like aquifers. The study said high potential, but also hurdles.
That's right, porous rock. Think of things like sandstone, Porosity just means how much empty space or pores the rock has to hold fluid, or in this case, air.
Like a sponge, sort
A
of.
very, very hard sponge,
Yeah.
yes. So this study assumed a minimum porosity of 13% was needed for city to work well. And these porous rock reservoirs, especially saline aquifers filled with salty water, are identified as potentially the least cost storage option for large-scale CAEs.
Least cost. Even cheaper than salt.
Potentially, yes.
Yeah.
The estimate was around 110 USD per megawatt hour for progressive storage.
But you said hurdles. This raises that important question. If it's potentially the cheapest, why aren't there any commercial CES plants using aquifers right now?
Good question. And the study touches on this. It briefly mentions a project in Iowa, the Iowa Stored Energy Park, which was planned for an aquifer but was terminated back in 2011 due to geological issues discovered during detailed site investigation.
So the geology turned out to be trickier than expected.
Exactly. It really underscores that even with promising large-scale potential, you need incredibly detailed site-specific analysis to make sure it's truly suitable and safe. You can't skip that step.
So which porous rocks work best?
Suitable ones include sandstone, some shales, limestone. But the study notes rocks like dolomite and quartzite are generally not suitable, probably due to lower porosity or other issues.
Okay, so cautious optimism for porous rock needs careful checking. What about the third type, hard rock?
Hard rock like granite or limestone. Development costs here are generally higher than for salt because you typically have to mechanically excavate the cavern rather than dissolving it.
So more digging, more expensive.
Usually. But there's potential cost saver. Using existing abandoned mines. If you can find an old limestone mine, for example, that's structurally sound and in the right place, it can significantly cut down those excavation costs.
Like the proposed Norton CAS plant in Ohio. I think I read about that.
Exactly. That's the plan there, repurposing an idle limestone mine. The study identifies granite as a particularly favorable hard rock for creating stable underground caverns. And even with higher initial costs, CAES in hard rock was still documented in this study as a potentially low-cost storage technology overall, especially if you can reuse existing infrastructure.
Interesting. And just quickly, are there any other geological options?
Yes, we shouldn't forget depleted natural gas and oil fields. These are already proven structures for storing gases. Companies have been storing natural gas in them for decades, so they're definitely viable candidates for CAs too.
Right, using existing infrastructure again. Okay, let's get to the really big numbers because this is where the scale of this just becomes, well, almost hard to grasp. What did this study reveal about the global potential of CES?
Okay, prepare yourself. This is the headline finding. This study found that a staggering 6,574 terawatt-hours, that's terawatt-hours of CES storage capacity, is available globally.
6,000.
6,574 terawatt-hours. And that's using their conservative 1% constraint we talked about earlier.
That number is just huge. How does that compare to what we actually need for, say, a fully renewable energy system?
Right, let's connect it to the bigger picture. For a hypothetical 100% renewable energy scenario globally by 2030, estimates suggest we need somewhere in the range of 4,900 to 5,800 terawatt-hours of storage throughput annually.
So the potential identified, even at the conservative 1% level, is actually more than the total estimated need for a fully renewable world.
Far more. That's the monumental takeaway here. The total global geological potential for CES massively exceeds what's required, even for a complete transition away from fossil fuels. The geology itself, the physical space underground, it is absolutely not a major constraint.
Wow. The Earth itself is a giant battery bigger than we need. That's a game changer in how we think about grid stability.
It really reframes the problem, doesn't it? It shifts the focus from, can we find enough storage, to how do we tap into what's already there?
Which regions did the study identify as having the most potential? Who are the leaders?
North America actually leads the pack, with about 0.26% of its total land area deemed suitable. And the study attributes this mainly to huge salt deposits and favorable geology.
Okay, North America #1. Who's next?
Sub-Saharan Africa follows pretty closely at 0.20% suitability, rich in both large aquifer reservoirs and salt deposits. Then South America comes in third at 0.19%.
Are there any specific hotspots within those regions, like standout areas?
Yes, a couple were highlighted. Western Canada apparently holds the single highest geological potential globally, estimated at 392 terawatt-hours of throughput.
Wow.
And within the U.S., the Mid-Atlantic region showed particularly high suitability, over 0.8%, which is significantly higher than the continental average.
Interesting. And just remind us, this was all based on the 1% rule. What if we used more of the suitable land?
Right, if we relax that constraint, if, say, 5% of the identified suitable area could be used, the potential just skyrockets to nearly 33,000 terawatt
And
hours.
400% increase.
Exactly. And if you went to 10%, it jumps to over 65,000 terawatt hours, a 900% increase from the baseline 1% estimate.
So the potential is just immense, almost limitless from a practical standpoint.
From a purely geological resource standpoint, yes.
Yeah.
It strongly suggests CS can play a critical, very large-scale role alongside batteries and pumped hydro. The Earth has provided the space.
Okay, so we have this incredible potential mapped out. How did the researchers check their work? Did they validate these findings somehow against real-world data?
They did. They performed a clever sensitivity analysis. They used existing data on underground natural gas storage facilities in the U.S., assuming reasonably, I think, that sites proven for gas storage would have similar geological suitability for CES.
Okay, using gas storage as a proxy, how did they compare them?
They looked at how well their predicted CES suitable locations overlapped with known natural gas storage sites. They used 3 scenarios. An optimistic one, CES site within 100 kilometers of a gas site. A moderate one, within 50 kilometers. And a pessimistic one, requiring direct geographical intersection.
And what did that comparison show? Did the predicted CES spots line up with the actual gas storage spots?
The results were pretty strong, actually, especially for salt caverns. Over 92% of the existing natural gas storage capacity in salt caverns overlapped with the locations this study identified as suitable for CES. And that was across all scenarios, even the pessimistic one.
That's very high agreement.
Very high. Depleted gas fields also showed good overlap, around 75%, even in the pessimistic direct intersection scenario. Aquifers showed the least overlap.
Why less for aquifers?
The study suggests this might be because their analysis focused on identifying large, regional-scale aquifer systems suitable for utility-scale CAEs, potentially missing some of the smaller, localized aquifers that might be used for natural gas storage.
Okay, that makes sense. So overall, how accurate did this validation suggest the study's main findings were?
Based on this comparison, the analysis confirmed the accuracy of the potential estimates to be somewhere in the range of 66–85% for total storage capacity and 63–82% based on the number of facilities.
That sounds pretty solid for a global estimate.
Absolutely. The study itself deemed it a solid starting point, giving a good level of confidence in the overall global picture they painted.
Bro, a good starting point. But mapping is one thing, building is another. What are the crucial real-world steps needed beyond just finding a spot on the map provided by this study?
Oh, absolutely crucial steps. This study provides the invaluable global overview, the big picture. But it strongly emphasizes that actually choosing and developing a specific site requires incredibly detailed, on-the-ground field studies.
Like what kind of studies?
We're talking comprehensive reservoir modeling to understand exactly how the air will behave underground. Detailed core sampling, drilling down and analyzing the rock itself. Looking closely at neotectonic activity, recent Earth movements or fault lines.
Seismic profiles.
Yes, seismic profiles to map the subsurface structure. Critically, addressing environmental issues like what do you do with the salty brine produced when solution mining salt caverns? And performing air injection tests to really confirm the cavern's integrity and how it holds pressure.
So a lot of detailed engineering and environmental work.
A huge amount. And perhaps the most critical practical factor, proximity. For a CA's plant to be cost-effective, the chosen site absolutely needs to be reasonably close to both the renewable energy source, the wind farm or solar park, and the existing electrical transmission grid to feed the power back in.
Location, 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 even underground.
Pretty much. These are the factors that bridge that gap from the vast theoretical potential shown in this study to actual working power plants.
Which brings us to this important question, maybe even a paradox. We've just heard about this vast geological potential, the clear technical advantages, especially with ACS. We know plants have operated for decades. So why? Why are there still only a handful of large-scale CAS plants actually running in the world? It seems baffling.
It is a bit baffling on the surface, isn't it?
Yeah.
Part of the historical answer is that pumped hydro, PHES, has often been more cost-efficient for storing bulk energy, especially the excess from old-style baseload plants like nuclear or coal that couldn't easily ramp down.
Okay, so PHES got the early investment.
Largely, yes. But as we've discussed, the game changes with variable renewables. The need for flexible, large-scale storage like CES becomes much more acute. So what's holding it back now?
Yeah, what did this study identify as the key barriers today?
This assessment highlights three main constraints currently impeding wider CACS. First, high upfront investment costs. Building these large underground facilities is expensive initially.
Big capital expenditure.
Exactly. And the study suggests this points to a need for, and I quote, reform of energy market and energy policies. Things like market mechanisms or incentives that properly value long-duration storage and help de-risk that initial investment.
So policy and market structure is one barrier. What else?
Second, there's a perceived risk, particularly among utilities, associated with underground geology and the field studies needed. Even though, as the study points out, the oil and gas industry has been successfully and safely storing hydrocarbons underground in similar formations for many, many years.
So it's maybe an unwarranted perception of risk?
Arguably, yes, or at least a risk that is well understood and manageable with proper expertise, which already exists. It seems there's a knowledge gap or perhaps a comfort zone issue within the utility sector compared to, say, geological engineers.
Interesting. And the third barrier?
The third one is maybe the most surprising, given the potential we've just discussed, a simple lack of awareness. The study bluntly states that very few utility engineers are aware of the great potential of CAEs available globally.
Wow. So the people who plan our grids might just not even know this is a serious option.
Apparently, that's a significant factor, according to this research. The knowledge about this vast potential just hasn't fully permeated the industry where planning and investment decisions are made.
That's kind of mind-blowing, that a solution of this scale could fly under the radar. It says a lot about inertia, maybe, or communication between different fields like geology and energy planning.
It certainly suggests opportunities for better education and cross-disciplinary communication.
So looking forward then, what's the outlook? What does this study suggest about the future, especially for that advanced ACS?
The study is ultimately very optimistic, particularly about ACEs. Remember, 70% efficiency, no fossil fuels. And importantly, it projects that the capital costs, the CapEx, for ACEs are expected to decrease over time as the technology matures and scales up.
So it gets cheaper as we build more.
That's the typical technology learning curve, yes. And the study makes another crucial point. CAES has insignificant material limits. Unlike some battery technologies that rely on materials like lithium or cobalt, which have supply chain or resource constraints.
CAES just needs rock and air, essentially.
Pretty much. Air, water, and suitable geology, which, as we've seen, is abundant. This lack of material constraint makes it incredibly promising for truly massive-scale, long-duration grid storage. It really could be the Earth's hidden battery.
So to wrap up, we've taken a deep dive today into this specific research, the assessment of geological resource potential for compressed air energy storage in global electricity supply. And what we've uncovered is this genuinely vast, largely untapped resource beneath our feet.
A resource that could fundamentally change how we store and use renewable energy.
Exactly. CAES, especially that advanced efficient ACS, really stands out. It's powerful, it's potentially environmentally friendly, and the geological capacity is globally abundant.
It's clear the technical know-how is there, or rapidly developing, and the geological potential is, frankly, overwhelming. The Earth seems ready to store our renewable future.
So maybe here's the final thought for you to consider. If the technology works, and the planet has provided vastly more storage space than we even need, what kind of innovation is truly required now? Is it technological, or is it more about the innovation in policy and market design, perhaps even just an awareness and societal will needed to finally unlock the full promise of this hidden global battery?